Okay guys, today we're going to go over background to Ohm's law and electrical power. We're going to start with electric current. So when we have an electric field, E, and we have maybe a proton in this field, the proton feels a force in the direction of the field. We've covered this last week. It feels a force in that direction and it will accelerate in the direction of the electric field. If we have an electron, then the electron will feel a force opposite of the electric field and accelerate in that direction. In the context of our class, we will be using circuits. So if we have a resistor, and then here we have an electric potential of 5 volts, and here we have an electric potential of 3 volts, then we have an electric field that points from the 5 volts to the 3 volts. And that will accelerate electrons from low to high voltage. It doesn't accelerate the protons because the protons are stuck where they are because they're in the metal. Like, if the protons could just move, my body would just disintegrate and fall apart and stuff like that. So, here we have an electric field that will put a force on these electrons and move them across. These moving charges is called a current. So we have all these little electrons moving to the left. Then we get a current to the right. Current goes to the right, and current is in opposite of the flow of electrons, or in the direction of the flow of protons. So here we have electrons moving from low voltage to high voltage, and current going from high voltage to low voltage. If our resistor has a resistance of R, then Ohm's law states that the voltage across the resistor is equal to the current flowing across the resistor times its resistance. So maybe our resistor has a resistance of 3 ohms. Then we could use V equals IR to calculate the current. So we have a voltage difference of 2 time is equal to I times 3. And this gives us I equals 2 over 3. So this is the basis of Ohm's law. If we have a resistor and a current is flowing through it, the electric power absorbed by this resistor is equal to I times the voltage across the resistor. And the voltage across the resistor is IR from Ohm's law. So this gives us I squared R. And we could also use I equals V over R for. So these are 3 different versions of the equation that we have. Depending on the question, sometimes one might be useful, sometimes you might want to use the other. Okay, circuit diagrams. So in circuit diagrams, wires are straight lines. batteries, voltage sources, are drawn as one of these two. I always draw this one on the right because I don't want to draw the extra lines. I just prefer this one on the right. So if we had a 5-volt battery, or you had your power source and you set it to 5 volts, then this would be plus 5 volts, and this would be 0 volts. That's what we will call it. So the positive side is the longer side of the battery. Ideal voltage sources. These are like theoretical voltage sources that you have in your homework questions. They don't exist in real life. Ideal voltage sources have no internal resistance. So that might sound a little bit weird, but internal resistance is inside of all batteries. All conductors have a very small amount of resistance, or all batteries will have a resistance in them. So here, if we have a battery, a 5-volt battery, then it can have an internal resistance of maybe 0.1 ohms. And this is actually the whole battery. So for a real battery, this is what it looks like. And then this is that's an ideal battery. So ideal batteries, again, they don't exist in real life. In real life, we only have real batteries. But when we study physics, we like to use the ideal version. So if we have the power source connected to a resistor, then the diagram looks like this. It was just simply the power source and the resistor. Okay, on to breadboards. Breadboards are going to be one of the, or some people struggle with breadboards a lot, and some people do great with breadboards. Hopefully you do great with breadboards because they're very important. The breadboard is connected along here. So this is one long metal strip and then another long metal strip. So here it shows the entire equipotential surface. So here's one long metal strip, here's another long metal strip. That's these two at the end. So this is all one equipotential surface. All these are connected. Then here's one more equipotential surface. All these are connected. And then these ones are connected vertically like this. And you can see that here we have the plates running this way. And each plate is an equipotential surface. So if I want to connect these two resistors like this, then if I have a battery, here, then electrons will flow from this negative port through this resistor, then through the metal inside of the breadboard, and then to the other resistor, and then back to the battery. And the current is in the opposite direction of electrons, so the current flows from the positive to the negative through the resistor, then through the breadboard to the other resistor, and into the negative. So that's how breadboards work. If I had this resistor like this, and I tried to hook them up to the power supply like that, then it doesn't work because these two ends are connected underneath through the equipotential surface. So the electrons will travel straight from this negative into that terminal, and then instead of traveling through the resistor, the electrons will just skip by it and go straight through the metal underneath to the positive side of the positive terminal of the battery. And and which is why the battery reads 0 volts, because the potential difference between these is 0 since they're both on this equipotential surface. So this is one big equipotential surface, and then the current is 5 because there's 0 resistance on this metal underneath the breadboard. And so with 0 resistance, then your current will go towards infinity. So here, this breadboard, this image shows a power supply in series with the 4.7 kilo ohm resistor, which is the same exact setup as we have here. So this circuit diagram is the same as this physical circuit. These are equivalent. And then here, this image shows how to read the resistance of a resistor off of the resistor. So if we wanted to calculate the resistance of the resistor on top, we would use the 4-band. For the 4-band resistors, would have R equals 100, and then band 1 is green, which is 5, plus 10, and then band 2 is blue, which is 6, and then times the multiplier here, which is yellow, which is 10k ohms. So this comes out to, what is that, 560 kilo ohms, I think. Yeah, that's right. Right here. So that's the first one. And then for practice, here's the second one. We have R equals, so now we're doing this lower resistor. 100 times band 1 is red, which is 2, plus 10 times band 2, which is orange, which is 3, plus band 3, which is purple, which is 7, or violet, and then times multiplier, which is 1 ohm. So this should be 237 ohm resistor, which is the correct answer as shown here. So let's say we tried to find the current through the resistor in the circuit using Ohm's law. Then we would have voltage across the resistor is equal to the current through the resistor times the resistance of the resistor. The voltage of this battery is 5 volts. So the potential difference between this point right here and this point right here is 5. But this wire is an equipotential surface, and so is this wire. So that means the electric potential at this point here is the same as this point here. Electric potential at this point here is the same as this point here. So since these are 5 apart, then this is also 5 apart. That might be a little bit confusing the first time you ever do it, but I promise after you do it a million times, or even just a few times, it actually becomes very, very simple and straightforward. So that's the voltage across the resistor. We have 5 volts across the resistor, and then we want to know the current across the resistor, and its resistance is 4.7 kilo ohms. So from this we can calculate I equals 5 volts over 4.7 kilo ohms, which is 5 over 4700 amps. And this comes out to 0.00106 amps, which is equal to 1.06 milliamps. So if we were to measure the current through this resistor, then we should read 1.06 milliamps. Now let's calculate the power absorbed by this resistor. We have power equals the current through the resistor times the voltage across the resistor, which gives us 1.06 milliamps, and the voltage was 5 volts. this comes out to 5.3 milliwatts. Yeah. So again, it might be confusing right now, but we have tons of practice ahead of us. Whether that's a good or a bad thing, we'll be prepped for the quizzes by the time they come. Hopefully this makes enough sense for the lab tomorrow. So you have to know how all of these equations work and how to build a circuit on a breadboard from a circuit diagram, a simple circuit diagram similar to this, maybe one more resistor. And you'll have to know how to calculate the resistance from the resistance bands.